NEC Article 430.34 addresses the use of combined overloads on multiple motors that are mechanically interconnected and operate simultaneously. Specifically, NEC Article 430.34 broadly states that when two or more motors drive the same load through a common intermediate means, the individual motor branch circuit, short circuit, and ground fault protection can be provided by a single protective device. This device must have settings or ratings suitable for the combined load of all the motors. To apply this to a situation where there is a pump and an oil cooler, and they are mechanically interconnected and will operate simultaneously, it is permissible to use the original 15 horsepower overloads on the main motor. However, the settings must be adjusted to account for the combined load. Here is the procedure for adjusting the overload settings. Firstly, determine the full load current, or FLC, of the oil cooler motor. This information can typically be found on the motor's nameplate. Secondly, calculate the combined full load current, or CFLC. This is done by adding the full load current of the main motor to the full load current of the oil cooler motor. The formula is CFLC equals FLC of the main motor plus FLC of the oil cooler motor. Thirdly, adjust the overload relay settings on the original overloads to the calculated combined full load current. For example, if the main motor's full load current is 25 amps and the oil cooler motor's full load current is 2 amps, the combined full load current would be 27 amps. Therefore, the original 15 horsepower overloads should be adjusted to a trip setting of 27 amps. It is important to consider these points. Firstly, ensure that the overloads are suitable for the type of motor being protected. Different motor types may have different overload protection requirements. Secondly, the circuit wiring must be sized appropriately for the combined load of both motors. Refer to the NEC tables to determine the appropriate wire size based on the combined full load current and other relevant factors such as ambient temperature and conductor insulation type. Thirdly, the disconnect and starter must be rated for the combined load of both motors. Ensure that these components have sufficient ampacity and horsepower ratings to handle the combined load without overheating or failing. When sizing conductors, refer to NEC Article 310.15 which covers ampacity of conductors. Table 310.15b16 provides the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air. For example, for a combined full load current of 27 amps, using copper conductors with a 75 degrees Celsius insulation rating, you might need a number 10 American wire gauge conductor, which is an ampacity of 30 amps under these conditions. Always consult the NEC for the specific requirements and rating factors that may apply to the installation. For motor overloads, Article 430 provides comprehensive guidance. Specifically, 430.6 covers motor circuit conductor sizing, 430.22 addresses the sizing of conductors for a single motor, and 430.24 covers the sizing of conductors for several motors. These sections provide detailed rules and calculations to ensure the proper sizing of conductors based on the motor's full load current, duty cycle, and other factors. For example, 430.22 states that the motor circuit conductors must have an ampacity of not less than 125% of the motor's full load current. This is to account for the motor's potential to draw current above its rated full load current during starting and overload conditions. Overload protection is crucial for preventing motor damage due to excessive current draw. Article 430.31 through 430.40 cover motor overload protection. These sections outline the requirements for overload devices, such as thermal overloads and electronic overloads, and how to select and size them appropriately. 430.32 specifically addresses continuous duty motors and provides guidance on the maximum allowable overload protection based on the motor's service factor or temperature rise rating. Short circuit and ground fault protection are essential for protecting the motor and circuit components from damage due to fault currents. NEC 430.51 through 430.58 cover motor short circuit and ground fault protection. These sections outline the requirements for protective devices such as fuses and circuit breakers, and how to select and size them appropriately. 430.52 provides specific guidelines on the maximum allowable rating or setting of the short circuit and ground fault protective device based on the motor's full load current and code letter designation. For motor control circuits, Article 430.71 through 430.74 provide requirements for motor control circuits. These sections cover topics such as control circuit voltage, overcurrent protection, and disconnect means. Proper motor control circuits ensure the safe and reliable operation of the motor and associated equipment. For example, 430.72 requires that motor control circuits be protected against overcurrent by suitable overcurrent devices, such as fuses or circuit breakers. These devices must be sized appropriately to protect the control circuit conductors and components from damage due to fault currents or overloads. Motor disconnects are required to provide a means of disconnecting the motor from the power supply for maintenance or emergency purposes. NEC 430.101 through 430.110 cover motor disconnects. These sections outline the requirements for disconnect switches and circuit breakers, and how to select and install them properly. 430.102 specifies the location requirements for motor disconnects, requiring them to be readily accessible and located within sight of the motor and driven machinery. Grounding is essential for electrical safety and for providing a low impedance path for fault currents to return to the source. Article 430.121 through 430.130 cover motor grounding. These sections outline the requirements for grounding motor frames, enclosures, and other non-current carrying metal parts. 430.122 requires that motor frames be grounded in accordance with NEC Article 250 to ensure electrical safety and prevent shock hazards. When dealing with hazardous locations, such as areas with flammable gases or dust, special precautions must be taken to prevent explosions or fires. Article 430.141 through 430.147 cover motors in hazardous locations. These sections outline the requirements for explosion-proof motors, dust ignition-proof motors, and other specialized equipment suitable for use in hazardous environments. Always consult the NEC and other applicable standards for specific requirements and guidance when installing and maintaining motors in hazardous locations. These NEC articles provide a comprehensive framework for the safe and reliable installation and operation of motors and motor control systems. By following these requirements and best practices, you can ensure the safety of personnel, protect equipment from damage, and minimize the risk of electrical hazards. Remember to always consult with a qualified electrical professional for specific guidance and assistance with your motor installations. In addition to the NEC, there are other relevant standards and guidelines that may apply to motor installations. NEMA, the National Electrical Manufacturers Association, publishes standards for motor dimensions, performance, and testing. These standards can be helpful in selecting and applying motors for specific applications. IEE, the Institute of Electrical and Electronics Engineers, publishes standards and recommended practices for electrical engineering, including motor protection and control. These standards can provide valuable insights and guidance for designing and implementing motor control systems. UL Underwriters Laboratories tests and certifies electrical products for safety. UL listing indicates that a product has been evaluated and meets UL safety requirements. When selecting motors and motor control equipment, look for UL listing to ensure that the products meet recognized safety standards. Local codes and regulations may also apply to motor installations. These codes may specify additional requirements or restrictions beyond those outlined in the NEC. Always check with your local authorities to ensure that your motor installations comply with all applicable codes and regulations. Proper maintenance is essential for ensuring the long-term reliability and performance of motors. Regular maintenance tasks may include lubricating bearings, cleaning windings, checking connections, and testing insulation resistance. A well-maintained motor will operate more efficiently, last longer, and be less likely to experience failures. Motor testing and troubleshooting are important skills for electrical professionals. Common motor tests include insulation resistance testing, winding resistance testing, and motor rotation testing. Troubleshooting techniques can help identify and resolve motor problems quickly and effectively. Remember, working with electricity can be dangerous. Always follow safe work practices and use appropriate personal protective equipment when installing, maintaining, or troubleshooting motors. To energize and lock out the circuit before working on any electrical equipment. If you are not qualified to work on electrical equipment, consult with a licensed electrician. Using these guidelines and information will help ensure motor installations are done correctly. Firstly, determine the full load amps of both motors. This is found on the motor nameplate. Secondly, combine the full load amps by adding them together. Thirdly, select appropriately sized conductors and overcurrent protection. Fourthly, verify all components are rated for the voltage being used. Fifthly, properly torque all electrical connections. Sixthly, test and verify proper motor operation. Seventhly, document all work performed. These steps will guide any motor installations.